Good morning, everyone. I'm K. Paramkumar from HPD section. And I am here to tell about my Dsd topic, Digital System Design, Tech Talk topic. Tech Talk topic is and my topic is about EDA and quantum computing, symbiotic relationship. Introduction. Computing is potentially one of the most transformative technologies of our times. This is because it offers a new model of computation that is based on quantum physics and is fundamentally different from that of current systems that are built on classically laws and Boolean algebra. There has been a flurry of results recently that has provided credence to the thinking that the technology has moved from a basic science problem towards an applied science of engineering one. The field has progressed from proof of concept to demonstration of quantum integrated circuits with over 50 qubits. John Preskill coined the term noisy intermediate scale quantum. To this era wherein we are far from a universal quantum computation but have enough quantum states, albeit noisy, to potentially demonstrate quantum advantage in hardware. There are many physical realizations of digital quantum computers, including iron trap superconducting capsules, linear optical devices, among many others. There are two popular physical relationships are perhaps ion traps and superconducting qubits. Each has its pluses and minuses. Companies groups are betting on different realizations, and no one solution has won. The consider superconducting qubits as they can be fabricated in silicon using the same technology that we use to manufacture classically hardware today. Many consulting firms have started evaluating this technology and have put forward their projections 18 to 20. Boston Consulting Group BCG estimates the business of quantum computing will be about 2 to 5 billions by 2024, reaching between 25 to 50 billions by 2030. Its further projects that it will reach for 450 to 850 billion annually in due course. This indicates that in the near term, 3 to 5 years, the impact is likely to be in the border of the quantum chemistry, optimized machine learning, and in finance. The question is, what is the impact of quantum computing of EDA? EDA is unique industry in that it is perhaps the only field that can not only potentially benefit from the technology but also contribute towards fostering it. EDA has immense knowledge and skills when it comes to the problem of scaling to larger designs. This is due to decades of classical hardware design automation and algorithms that emerged from it. This can potentially be leveraged by quantum computers designers. The question is, what is the impact of comfort computing on EDA? EDA is a unique industry in that it is perhaps the only field that can not only potentially benefit from the technology but also contribute towards fostering it. EDA has immense knowledge and skills when it comes to the problem of scaling it comes to the problem of scaling to larger designs. This is due to decades of classical hardware designs, automation, and algorithm that emerged from Meta. This can potentially be leveraged by quantum computer designers. A general-purpose universal quantum computer can be achieved by the application of error correction and fault-tolerant techniques. This requires that a qubits where the information that we care about is stored at logical level and the physical qubits based on the encoding used essentially provides redundancy. The number of qubits required to achieve this is estimated to be in the order of millions. Also, error correction and fault tolerant techniques are only possible when we achieve an error bounded of 10 to 10 to 3 or less. We are orders the magnitude from the bond. Generally purpose universal quantum computation is therefore still years if not decades anyway. They exhibit some characteristics that needed to be accounted for any solution using them. Limited connectivity. The qubits in NISQ devices do not have connections to all qubits, so a two-qubit operation between distant qubits requires a series of swap operations to get them to neighboring qubits and then perform the required operation. Short circuit depth. NISQ qubits are noisy, which means that they will lose their quantum state in a reasonably short duration. This puts a limitation on the amount of compute that can be done uh, and the algorithm that we want to implement in hardware needs to fit into this and Kubert's noise variability. The noise characteristics of individual qubits vary and they are not equal. In fact, the noise characteristics of a given qubit can vary over time. Quantum volume, coherence, quotient, inheritance. Design a better chip. First here is the quantum chip itself. The first number of qubits is connectivity. Example, the coupling map and the equality and the quality of each connection are key parameters that determine QV. The key area of research is to come up with better coupling maps that allow for more qubits to be coupled with the less crosstalk, thereby ensuring that the qubits have a low error rates and along with coherence time. Conventional layout tools are generally well suited to lay out the chips for a smaller number of qubits. Manual layout has been sufficient, but now that we get into the design of 100 plus qubit chips, automation to generate promising topologies and faster simulation to pick the good candidates that are essential. Electromagnetic field simulators like HFSS are good for the detailed simulation but not necessarily fast enough to fuel the solution space of possible topologies. Static, static mapping, an area where EDA algorithm can play a key role in the mapping of algorithm to quantum circuits. Simple algorithm focus mostly on the connectivity map of the quantum computer since there are only a limited number of qubits and there is only a limited amount of time to complete the computation. Good circuit outcome optimization and mapping can make a huge difference to whether an algorithm can run on a current NASQ machine or not. Integration time, absent time, 2 QBO, single qubit in different countries. Circuit representation, A circuit representation, B representation in terms of CNITs. Swap gate is costly superconducting qubits like IBMs. as it takes three CNT gates to perform a single swap gate. Quantum Quantum deep learning, machine and deep learning have had big impact on business in the last decade and continue to do so. A data-rich domain like EDA is not immune to its perfect, and we are getting seeing many interesting developments on the front of recent times. On the quantum front, there is a new wave of results that have come about in the recent times that has pushed quantum machines learning as one of the important application towards for in an era. Quantum cellular definite programming, there are many problems in EDA that lends itself to be solved as a convex optimization problems. Brandon it will have recently discovered discovered a quantum approximate version of a semi-definite programming problem that has exponentially faster than the best known classical. One of the key aspects of the algorithm is the availability of an initial state that has a specific form. Thermal gives state and input symbiotic relationship. Quantum computing is very promising technology that it has its infancy right but now, but has potentially to disrupt many businesses in the coming years. The compute power quantum volume increase is following the potential trajectory increase is following as like more more loss and it's projected to be continued. We have entered in an age to era where we have only small number of hundred soft noisy qubits to do useful works. The challenge is to maximize the quantum value when quite some papers have been published that address optimization of individual matrices. They need to be optimized collectively to have a real impact on the quantum value. The EDA community has a long experience in optimizing for many conflicting objectives such as timing, area, power, and thank you.